So we physicists, we have this huge ambition, right? A kind of guiding light.
The theory of everything.
Exactly, the TOE. It's supposed to be this one single framework, yeah, that connects the big two ideas in physics.
The standard model that's particles and forces, but not gravity, and then Einstein's general relativity.
Which is our theory of gravity and, the universe at large scale. It's a pretty massive goal.
It absolutely is. And it's not just about finding any theory that works. There's this real drive for elegance.
Elegance? You mean like simplicity?
Kind of, yeah, simplicity, but powerful simplicity. We want explanations that, explain the most stuff with the fewest starting points, minimal assumptions, maximum explanatory power, like a really beautiful equation.
Concise, but tells you loads. Okay, I get that. That elegance, that's the driving force.
That's really. Which brings us to today's deep dive. We're looking at a really fascinating contender for this theory of everything.
Eric Weinstein's Geometric Unity, or GU.
That's the one. And our guide is this really great article, The Iceberg of Geometric Unity Comprehensive and Technical Edition.
Good title, Iceberg.
Yeah.
Because it really does start with things that feel a bit more familiar, the tip.
And then it dives deep, really deep into the technical stuff.
Right. So think of this this session as your shortcut through that iceberg.
Yeah. We're aiming to pull out the really key ideas, the most intriguing bits, without you getting swamped by all the heavy math.
Our mission, basically, is to give you a solid grasp of what geometric unity is actually about, its core ideas, and why it's causing a stir.
Why people are talking about it. Okay, so where does the article start? It lays out the current ingredient lists for physics.
Yeah, exactly. The recipe list of everything we're trying to unify. First up, Einstein. The Ricci tensor.
Okay, Ricci tensor. In simple terms.
It's the math for gravity, how space-time gets curved, bent, warped by mass and energy.
And that curvature is what we feel is gravity. So that's ingredient one. Why is it tough to unify?
Well, gravity's just different. It hasn't played nicely with the quantum descriptions of the other forces.
Okay, next ingredient.
The Yang-Mills-Maxwell action. Bit of a mouthful, but this covers the other fundamental forces.
Strong force, weak force, electromagnetism.
Right. Strong force holds atomic nuclei together. Weak force does some radioactive decay stuff. And electromagnetism is, well, electricity, magnetism, light.
And this action describes how particles interact via those forces. The challenge being
finding a common language that includes gravity alongside these.
Got it. What else is in the recipe?
The fermionic action. This uses things called Dirac operators.
Okay, and those describe?
The fundamental matter particles, electrons, quarks, the basic building blocks.
So unifying the force rules and the matter rules plus gravity. Big job.
Huge. Then there's the Higgs mechanism.
Ah, the God particle stuff. How particles get mass.
Pretty much. You can sort of imagine particles moving through this cosmic field like molasses.
And the more they interact, the more sticky they feel.
Exactly. That stickiness, that resistance, that's what we perceive as mass. And fitting that neatly into a unified picture is another hurdle.
Makes sense. Keep going.
Okay, spin groups. Specifically SL2C. Sounds technical.
It is, but it's essential for describing a quantum property called spin.
Like particles having their own little built-in angular momentum.
That's sort of, yeah. It's a purely quantum thing. And again, bridging quantum mechanics and gravity.
Yeah.
That's the major problem we keep hitting.
Right. Next.
The gauge symmetry group, SU3, SU2, SU1. Don't worry too much about the name.
Okay. What's the idea?
Think of it as the deep down mathematical pattern behind how the strong, weak, and electromagnetic forces work and relate to each other. The symmetry underlying them.
Like their operating system.
Yeah, maybe like that.
Yeah.
The puzzle is how that pattern connects to the geometry of space-time, to gravity.
Okay. Nearly done with the list.
Almost. We've got family quantum numbers and generation.
Oh, this is the thing where we have like 3 versions of particles. Electron, muon, tau.
Exactly. Those are the lepton generations. Quarks have them too.
Yeah.
It's weird, right? Why these copies?
Yeah, why 3? A really good theory of everything should probably explain that.
Ideally, yes.
Mm-hmm.
And finally, the CKM and PM&S matrices.
More math. What do these describe?
They describe how certain particles, quarks, and neutrinos can actually change into each other, transform.
Whoa, okay. That adds another layer of complexity.
It does. So a unified theory should, ideally explain these transformations naturally too. That's the current setup, the ingredients we need to combine.
Now, the article points out something interesting about our main tool for particle physics, quantum field theory, or QFT.
Yes, as QFT has historically leaned really heavily on mathematical analysis, like calculus.
And maybe hasn't focused as much on geometry and topology.
Exactly. And the interesting bit is that some weird things in physics like anomalies, where rules seem to break down, or conservation laws.
Things like conservation of energy or charge.
Uh-huh. Those things, and even some non-local effects, can actually sometimes be explained much more, well, naturally using geometry, using shapes and connections.
More elegantly.
Potentially, yeah. It suggests geometry might be a more fundamental language for some of these deep phenomena.
Okay, so that whole discussion really sets the stage for geometric unity, right? Because GU is all about geometry.
Precisely. And the big idea, the core shift, is that instead of starting with space-time already set up, with a fixed way to measure things.
A fixed metric, you called it.
Right. GU starts somewhere more fundamental. It doesn't pick one metric first.
Okay, so what does it start with? The article has these neat little summaries, GU in 4 words.
Einstein knows Patti Salam.
Intriguing, what's that telling us? Toddy Salam's another unification theory, right?
Yeah, Patti Salam tries to unify some of the forces and particles within the standard model itself in a more symmetrical way. So Einstein knows Patti Salam is like saying GU aims to connect Einstein's gravity.
With this more unified picture of the other forces and particles, a grander unification.
Exactly. It's packing a lot of ambition into 4 words.
Okay, then there's the 30-word version. General relativity is leveraged to unify the standard model's first generation by pulling back structures, specifically Weil-Spinors, from a specially constructed space of metrics. Whoa, okay, let's break that down.
All right. First part. Unify the standard model's first generation.
So the up and down quarks, the electron, and the electron neutrino, the most basic familiar ones, why just the first generation to start?
Well, it's strategic. Nail the foundation first, right? If you can unify the simplest set, maybe that shows the way to unify the heavier, more complicated generations later.
Makes sense. Start simple, and it says leverage general relativity. So Einstein's theory isn't thrown out.
Not at all. It's actually a key tool. GU is looking for a deep link between the geometry of GR, space William curvature, and the structure of the standard model particles.
As if the particle properties might somehow emerge from the geometry.
That's the kind of idea, yeah. Deriving particles from geometry, in a way.
Okay, now, the really tricky bit. Pulling back structures from a specially constructed space of metrics. What does that mean intuitively?
Okay, imagine you have like a really complex, intricate blueprint on one sheet of paper. That's the specially constructed space of metrics.
Right, some fundamental space.
And you want to understand a simpler pattern on another sheet that's our familiar particles and forces. Pulling back is like a mathematical way of projecting or deriving the simpler pattern from the more complex blueprint.
So the properties of electrons and quarks, these Weil-Spinors it mentioned,
Which are just mathematical objects describing the particles.
they're somehow derived from this deeper geometric space.
That's the core idea. Their properties aren't fundamental in themselves. They come from this underlying geometry of metrics.
And the starting point, the absolute base, is still our familiar 4D spacetime. 3 space, 1 time.
Yep, the stage is still our 4-dimensional universe. That doesn't change.
But then comes the crazy leap. Instead of just that one spacetime with one fixed metric.
GU considers, well, all of them, all possible metrics.
All possible ways to measure distance and time everywhere all at once.
Essentially, yes. It considers the bundle of all possible metrics over our 4D spacetime. And this bundle turns out to be a 14-dimensional space. Why 14?
No. 14 dimensions. Why 14?
Okay, so in 4D, the metric tensor, the thing defining distance, has 10 independent numbers components needed to specify it at any point.
Right. 10 degrees of freedom for the metric itself.
Uh-huh. And you have those 10 possibilities at every point in our 4 dimensions of spacetime. So it's like 10 dimensions worth of metric possibilities layered over the 4 dimensions of spacetime.
10 plus 4 gives 14. Wow, why consider all metrics at once? What does that buy you?
Well, standard theories usually pick one metric right at the start. GU says maybe that's putting the cart before the horse, maybe the geometry isn't fixed.
It avoids choosing up front. Could solve some problems.
Potentially, yeah. There's this kind of chicken and egg issue about whether space-time geometry defines how particles behave, or if particles define the geometry. By starting with all geometries, GU hopes to find a more fundamental origin for both.
The article also mentions something about operator analogies, differences between how force theories and gravity handle things.
Yeah, it's getting into the weeds a bit, but essentially, the mathematical tools, the operators, used in Yang-Mills theories and general relativity. They treat things like symmetry transformations slightly differently.
Little inconsistencies.
Subtle ones, yeah. And it mentions the twin origins problem, which seems to point at deeper issues in how we even define fundamental things in our current theories. GU is trying to smooth out these foundational wrinkles.
So the grand dream here is to start with just this space of all possible geometries,
Which sounds complex, but it's built on fairly minimal geometric assumptions.
and from that minimal starting point, derive all the complexity we see, the standard model particles, the forces, the generations, the mixing, everything.
That's the ultimate ambition. The article uses the analogy of DNA.
Yeah.
Right? Just four simple bases.
Giving rise to the unbelievable complexity of life.
Exactly. GU hopes for a similar kind of emergent complexity from a simple, elegant geometric foundation.
It really makes you appreciate the limits of what we currently know, doesn't it? And how crucial this advanced math differential geometry topology is becoming for pushing physics forward.
Absolutely. It shows where the frontier really is right now. It's deep in the mathematical structure of reality.
Okay, so let's try and wrap this up. Geometric unity, it's this really audacious attempt to redefine physics from the ground up.
Instead of a fixed reality, start with the geometry of all possibilities.
Right, and use that to elegantly unify gravity with the standard model.
It really does make you stop and think, what if the key isn't just finding a specific metric, a specific state of the universe?
But understanding the landscape of all possible states, what could that tell us about space-time, particles?
Exactly. What new perspectives open up? It's a very different way of thinking.
And look, GU is obviously super complex. It's still evolving. Lots of work to be done.
For sure, it's cutting-edge theoretical physics.
But even just grasping the core ideas, what it's trying to do, gives you a real insight into where the search for a complete understanding might be heading.
Definitely. And if you are intrigued and want more of the mathematical meat, the article link is there for you to dive even deeper.
It leaves you with a pretty profound final thought, doesn't it? Could it be that the ultimate secrets aren't hidden in finding more particles?
But in figuring out the fundamental geometry of reality itself.
Definitely food for thought.